Welcome to the Basic Electrical Engineering lectures. Here our objective is what is the instantaneous power waveform for the R, L and C different loads. We are giving the same supply voltage so that the reference is same, and also we have obtained in the previous video what is the value of current for the resistor, for the inductor and for the capacitor. Now we will try to evaluate the power, instantaneous power for all the three cases, and then we will see the waveforms. So we have just written the value of the power for the resistive. We have just multiplied the value of V and I, and in three cases got the value of PR, PL and PC. Now we have to just evaluate this equation and try to split it into two different forms or one form so that we can have a realistic example. So here we have written just divided by 2 and get the multiplication with 2 in all the three cases. Now we use a trigonometric expression that 2 sin A sin B is equal to cos of A minus B minus cos of A plus B. So we can rewrite this as, let us take this term as V is equal to Vm by root 2. So if we split this term as Vm by root 2 into Im by root 2, root 2 into 2 is 2, root 2 into root 2 is 2, and 2 sin square theta is 1 minus cos 2 omega t. This is what we get here, the power equation. Similarly for the PL power across the inductor, this is equal to IML by root 2. This term will be in this way, the PL is equal to cos of A minus B minus of cos of A plus B. So obviously this term will be 0, cos 90, this term will be 0. Similarly we can write for the power across the capacitor. We got the value of this as cos minus of 90 because of A minus of B, omega t minus omega t plus 90, this term, but still this term will leads to 0 because this is cos of 90, so this term will be 0, and you have left out with minus of cos 2 omega t plus 90. So we got all the values, so let me rewrite again. So we get the value of this as same as this one, only we replace by V and R, IR here, and just in capital letter these are the RMS quantities. Here also we get it negative because of this minus sign, and rest of the things we rewrite again. Here also same negative, and rest of the things again. Let us can we make it more simplified? We try to convert this cos to sine, and here also from cos to sine, and get the minus sign like this. And if I write in terms of sine, we just add whatever the value over here plus 90, same whatever the value over here plus 90. Now this negative sign also, let us remove it and write in appropriate way. So for negative sign we just add here minus 180 on both the sides, and we keep here not distributing in terms of sign or something, just because this is the positive quantity seems to be, so we will have a waveform analysis of it. So here what we get is the value of PR we can rewrite again, VIL, and this term is cancel each other. This is sine of 2 omega t minus 180, and this side will be VIC sine of this 2 will cancel, and here this is only 2 omega t. This is the value of PC what you get, here PL what we get, and here PR. So what we can think this is as equals to VIR, fixed quantity, minus VIR cos of 2 omega t. If you want to split that also, you can split it as VR minus of VIR. Instead of this cos, you can have 2 omega t plus 90. Then you can have this negative sign, you can remove, then VIR minus VIR or plus, okay, this will be sine of, we can say whatever term, minus 180. So this will nothing but this term minus 180 plus 90, it will be minus of 90. So we get the instantaneous value PR, we get here instantaneous value PL, and we get here instantaneous value PC. So here we have drawn for the simplicity the sine waveform only. This is a reference waveform, sine waveform, so that we can draw the other waveforms looking at this waveform here. So here it's like sine 2 omega t. So sine 2 omega t means what? Here you have got a waveform which frequency is twice the frequency of the normal waveform. So here the frequency is in omega, but here it is 2 omega. So the time period is reduced, and now the same waveform will be reflected in from 0 to pi. So let me try to draw here one waveform which is having the frequency twice the frequency of the normal sinusoidal waveform. So this is how we can draw a frequency which is twice the frequency of the normal sinusoidal waveform. And this waveform we can give a name. Let us say this value is this value, which is the quantity. This quantity is multiplied with a sine term. So where this overall quantity is the instantaneous value and the maximum value of the power. So I can say this magnitude over here is the maximum value, and this value is equal to VIC. One thing, and another thing, this instantaneous value is given by this, PC is given by this. So in one cycle it is twice it is having a positive value and twice it is having negative power. So we can say that during the positive power it is absorbing the power, then the power is getting given back by the source, because this is represented by the capacitor. So when it is the power is positive, the capacitor is absorbing the power, and when the power is negative, the capacitor is like giving back the power. So now for this value of PL, this is the term, it is minus by 180 degree, and this term, if we take this term is equal to 0, so we can write why we are adding, so that we can know that when this waveform is going to start. So from here we get this is as omega t equals to 90 degree. In 2 omega, double the frequency, it is subtracted by 180. That means from omega t equals to 90 degree, this waveform will be starting in the scale of omega t here. So the sine 2 omega t, this waveform will start at omega t equals to 90 degree. So you will get a waveform like this, and here so you get the waveform, complete waveform of the sine 2 omega t after a phase lag of 90 degree. So you can observe that how the PL is being obtained, and then you can obtain here the rest of the waveform you can draw. Here also rest of the waveform you can draw. So this gives you the value of PL, and this magnitude, what you can see here, this magnitude is obviously is equal to VIL. You can also write that this magnitude is VM IML by 2. This is the same thing, so not to be confused, whatever the magnitude over here, this has to be the peak value, so that is why it is a peak value, and this is what you get. So in inductive load, it is like you have an inductive load, so power is getting relieved first, then first the negative power is there, then you have a positive power, so power is getting absorbed after that. So when we take the value of the power for PR, there is also sine of 2 omega t minus 90 degree. So we can evaluate it like it will have a omega t equals to 45 degree. The lag is there at 45 degree in the omega t scale. And what we can know is that we can have, this is the peak value, of this waveform. And since another value is there, like we can have, this is VIR, the same value is there, so we can have a combination of these two, and we can say 1 plus this sine of 2 omega t minus 90. So what we can do is we can give a like biasing to it, like this waveform maybe let us say starting from this line, and so that we can have a clear picture out of it. And at 45 degree we make a mirror imaging on here so that we can draw the waveform. So now at 45 degree lag you have got a sine waveform. So the sine waveform we will draw with a 45 degree lag. This is the 45 degree lag. We will try to draw the sine waveform. Now we can see that the sine waveform is drawn with the 45 degree lag, and let us complete that like this. So the same waveform, and we just intentionally make that let this height be this small height, because the sine waveform we are trying to make from this line. So let this height is VIR, and we give a biasing to it, imagining that this height is also VIR. Now we have got this waveform, and what we get is that whatever the value of omega t, this will always be a positive value. At omega t equals to, this is 180, this is 90 degree, and this is 360. At omega t is equal to 180, we can have sine of 360, 180, 360 minus 90. So sine of 360 minus 90 is sine of minus 90, and that value is minus of VIR. So you can check that value. VR at omega t equals to 180 degree will give you VIR minus of VIR is equal to 0, and at omega t equals to 90 degree, this two value can add up and you will get 2 VIR. So this height will be 2 VIR. So like that we understood and try to evaluate what will be the power waveform for the R type of load, and for the L type of load, and for the capacitor type of load. We can also plot the voltage and current waveform along with it. We will see. So we have drawn the structure of this so that we can draw the waveform smoothly. So let us draw the sine waveform with this taking this height as peak value. Okay, now we have got a sine waveform ready for this, and the current waveform will be the same height. So the current waveform will be of same phase of the voltage waveform, because here we have the V is equal to Vm sine omega t and I is equal to Im sine omega t. So both the current and power voltage waveform will be like this, and the power of waveform, obviously V into I is the power, which will give you some value multiplication of these to voltage and current. And obviously when power and voltage and current both are positive, you will have got the power value as positive. Here if both are negative, you will have the power value will be always positive. So you got a waveform. Only thing is that here in the look wise it looked like two wave upward, and here also you get the power waveform look like this. Maybe because of the drawing the picture is not the similar, otherwise both reflecting the power as V into I. So similarly we can draw for the inductor and capacitor. So the structure has been created so that you can easily see that you have a voltage, and the current is made omega t minus 90. At 90 degree it will start, so the current is lagging. So if we draw the other part of it, you can see that this is the way it will going to reflect in the waveform. And here it is omega t equals to plus 90, so it is omega t at minus 90 it will start, and the waveform look like this. with this dotted lines. Okay, so now we have the voltage and the current waveform both ready. Okay, this magnitude wise we can decrease a little of so here we can draw the current. This is the current and the voltage waveform. Okay, so let me draw it here. So you have the voltage and current, so let us draw the power waveform. So power here is that voltage and current both are opposite. So voltage is positive, current is negative. So you have obviously the power is in the negative one. Here voltage and current both are positive, so obviously the power is. So I'm making a little bit of height more so that it is clear visible. So this is what it is, power is positive. Okay. And then we have here the current is positive and the voltage is negative. So again the power is -1. And here one thing is that if we see the magnitude wise, both the power for the positive and negative is equal magnitude. So considering that equality, so let us draw in that way, because you have the equal value of like negative and the positive values. So here you have first positive, so let me take this height so that it is easy to draw. Okay, and here we have got a waveform like this. So now if we see that this diagram that we have drawn earlier, it is matching with it, because here also the same concept is being used, like power, voltage, current, and this will be the power PL and this will be power PC. And the reason of this current lag is plus 90, current lead is plus 90, and here it is lag is minus 90. So we have got this from VI. We can also get the waveforms, and also we can get the waveforms from the power equation that we have obtained in this way for the capacitor, for the inductor, and for the resistor. So this is the understanding of the power concept. Thank you very much. In the next video we'll learn a different thing.